Hello, do you hear me? Hello, do you hear me?
Yes, sir.
I upload another class material inside this. Can go to file and class material to see the new document. And we talk about type architecture. So which is today lesson. We are going to have two exercise after that. So, and the exercise you can find it in the ebook as well. All right, so we can start now. From the last session, we have done about the review, what you have learned so far during your third year. And for now, we continue from what we have done. And for this full lesson, we will focus on the memory architecture. And inside, when we talk about the memory architecture, there are a lot of sections inside. We can split it into three different levels. First, about the register, which is a part of CPU, and I don't think we need to cover it again because it's already inside the CPU lesson from the previous year. And there are two remaining sections which is related to the memory architecture. One is about the cache, another one is about the virtual memory. Virtual memory here is related between primary memory and secondary memory. So it talk about what is the communication, how data is structured, how data is moved between primary memory and secondary memory. And about cache here is the relationship between primary memory with the CPU itself. So in this lesson, we are going to learn about the cache. All right. All right, so here is the schema that you can, what you see here is a schema about the memory architecture. Like I mentioned before, we have the register, which is located inside the processor, the cache memory, and the primary memory. And when you call it DRAM here, because the primary memory is normally built with the dynamic RAM. Do you remember about DRAM, SRAM, SDRAM? I hope you still remember about it. DRAM or SRAM is about the physically how it is made. Normally SRAM is quite faster than DRAM, but it is more expensive, so they use SRAM mostly for the cache. And DRAM is it's faster comparing to the secondary memory, but it's still slower comparing to the SRAM. That's why normally we made RAM with the DRAM. Something like the DDR2, DDR3, DDR4, and the last one, the later version of the DDR5. They are still built with the DRAM. So here is some memory hierarchy, but actually we miss another one after the DRAM, which is the secondary memory. But as in our lesson, we focus on the relationship between the DRAM with the processor. So here we only draw what we are focusing on. All right. So here the DRAM is a light memory, but it is slow comparing to the SRAM. And the SRAM is smaller, but it's faster. So we build cache with the SRAM and DRAM we use for RAM, for primary memory. And then, so how can we make the access time faster, smaller, I mean? To do that, we need to make sure that all the data flow, or maybe you say all the requests from the processor can be handled mostly by cache, by the small RAM here. Okay, you need to know that cache or primary here, even they are different in physically. Even cache is built with SRAM and primary memory built with DRAM. But the purpose is still the same. They are used to store application, used to store data which is required by the processor. All right? It's just that for cache, it's just a part of the primary memory. That's why if you want to improve the data, you need to make sure that the processor can access to the data that it requires, and it can be found in the cache. So that the performance of the overall application will be a lot faster. Okay. Here just some like I told you before in the previous slide. So it's just some comparing between the memory. And here is about, you can see the some kind of real data or some practical data that you can compare with. The register located inside where, what is the size in average, something like 100 bytes like this, which you see. Register is very small, mostly it's about 100 bytes at most. And the speed is quite fast, you can see it here, less than 10 nanosecond. Actually here 10 nanosecond, not 10s and nanosecond, all right? And then you can see cache, and cache speed is about 10 to 100 nanosecond. And then memory is about 100 nanosecond to 1 millisecond. And then the disk and then the tab. So comparing the speed and size here, just some kind of evidence to show that which one is faster, which one is slower. So coming here, we talk about the principle of locality. The principle of locality here, what you see in the graphic here, you can see in the Y bar is the probability of reference, and the address space in the H bar, axis bar, okay? So with this graphic, what hello, Lưu dùng gì ạ?
Lưới chờ.
Lưu chứ ba hả?
Yes,
Các
sir.
bạn internet nhau vì bệnh sản bệnh. Okay, so let's resume again. Share screen long this. Tell me if you cannot hear me or you cannot hear me clearly because I'm not on hotspot. Not sure. So you hear me and you see the slide presentation, right?
Yeah, see, teacher.
So coming back to the question here, what is the graphic represent? Can anyone tell me what do you think about the graphic? The Y bar here, you see the probability of reference, and the H bar here is about the address space. So let me tell you a bit about what is the probability of reference. The probability of reference here refer to the amount of the CPU make request to memory. All right. So here the hello. I'm really sorry, guys, about the internet. I'm not sure what's wrong when the phone doesn't work well, but I think it should be fine now. So let's try it again. If it's connected again, we have no choice but need to change. Yeah, but I think it should be fine now. Let's try again. Okay, sorry for the inconvenience. Okay, so let's just skip this question. I just continue the explanation. You hear me right now?
Yeah, here, teacher.
Okay, good. So we continue. I try to ask question, but okay, let's just I will answer the question here. So in the graphic here represent that the amount of CPU make request to memory comparing to address space is only at the same. You can see the spike peak, the peak point here. You can see here from 0 and until this section, it has nothing. It's close to 0. It means that CPU calling or making request to get data from the memory is not a constant request. It may request only at some period of time. Okay, so comparing the two terms and also comparing to address space. So some that address space doesn't need to have access. Also, some address space CPU doesn't need to get it. But at some point, in some part of the address space, when CPU may request, it will keep requesting until the block of the data. You see, that's why when the address space come into here, it keep coming, going to the peak, and then it coming to the bottom. It means that at that time, at the address space, a lot of request is made by CPU, and then there is an empty again, and then there is a peak request again, and after that there is empty. So with this graphic, you can tell that CPU may request to memory only at a part of the address space. It's not everywhere. It doesn't access to data in memory everywhere. It's just in some section of data only. Okay. So based on this graphic, we have designed. We have two concepts about the locality or reference. When you talk about locality or reference, you refer to how CPU may request to the memory. All right. So there are two types to concept of it. One, if you call it temporal locality, which is refer locality in time. If an item is reference, it will tend to be reference again soon. Okay. So if we access to an item at the time t, at the time t plus 1, the probability of that data will be accessed again is quite high. So this is called the temporal locality. Okay. Another one is about the spatial locality. Spatial locality here is talking about the address which is nearby the data that CPU is requesting. Imagine that CPU made a request to a data at address 100 in RAM. So the address 100 plus 10, for example, and 100 minus 10. So the address near that address 100 are having a lot of probability that the CPU will request at that address. Do you understand what I say? Okay. So we have two concepts here. One, we call it temporal locality, and second, we call it spatial locality. And these two types of locality is interpreted based on this real experiment, real graphic. All right. So when we design the cache, or actually it's not just about cache and also about the primary memory, we tend to reply to these two type of locality or reference. To do that, normally in cache, here is the cache, here in the memory, we group the data together and we call it block. BLK here refer to block H, and here is block Y. Block here refer to the grouping of data together, and you need to see to know that block in any kind of memory in any type of level need to be the same. If we are moving block from memory to cache, the same data, the same amount of data need to be applied. All right. So here block H and block Y right here have the same size. Here the block H has 8 volt or 8 byte. Block Y also have 8 byte. All right. Okay. So here you see the concept of block and why we need block. Because we want to use the two concepts that we show that you see in the previous slide, talking about the locality of reference and the special of locality. So the concept here is that when we CPU make a request to the cache here, and if the data is found in that cache, it will return the data to the CPU that there is the no more procedure. But if the data is not be found in the cache here, you need to find the data again in the main memory or the primary memory. And after that, we need to copy the data back to the cache, because we think that if data is accessed now, it tends to access again in the near future. That's why we copy the data back to cache. You see? So here we, because we think that based on the locality of reference, the locality of temporary locality, what I can call it here, temporal locality. If the data access now, it tend to access again in the near future. That's why we copy the data back into the cache. Another thing is that when we copy the data from memory to cache, we don't just copy that small section of data, but we copy the whole block of it. We copy the whole block that CPU that data of CPU requested located inside. All right. So because we think that based on the here spatial locality, if the data is requested now, data H plus 1, H plus 2, H plus 3, or maybe H minus 1, H minus 2, H minus 3, has a very high probability that the CPU will be accessed again. Do you understand what I say? That's why they create the concept of block data here. When the data is not be found in cache, and the data need to copy into the cache, it doesn't copy just the data that it missed, but also the whole block that the data is reside on. Okay. So here is some keyword in the lesson that you will see it very frequently in the future. There is about hit, miss, and hit time. Hit here refer to when the data is found inside the memory. It can be in cache or it can be in RAM. But the point is, if the CPU can find the data it requires, we call it hit. Okay? Request is hit. But if the data is not found inside the memory or maybe inside cache, we call it miss. Okay? The request is miss. So in the future, if you see that the request is missed, it means that the CPU is making a request to some level of memory, but it cannot be found. Okay. When we talk about hit, we can have hit rate and hit time. Hit rate is kind of the percentage, like you request CPU make 10 requests to cache, and it can find five requests of that 10 requests can find the data it requires. So the hit rate is 50%. All right. And the same thing for here, the miss. If CPU make 10 requests and it cannot find 5 requests, so the miss rate is 50%. And if you apply the formula here, you can say 1 minus hit rate. Okay, 1 here refer to 100%, and hit rate. Okay. So if 100%, hit rate is 50%, so the miss rate is 50%. Okay. And then we have the hit time and the miss penalty. Hit time here refer to time to access the upper level with a consist of RAM, access time plus time to determine hit or miss. Okay. So when you talk about hit time here, it total the amount of to locate that inside the upper level here. Upper level here refer to catch. Okay. And then the transfer the data between CPU and cache. So we call it hit time. But miss penalty, the same thing with hit time, but it add additional time to replace the block. Because normally when the data it cannot be found in the cache, you need to replace it. You need to replace the block from memory. So when you are replacing something, you need time to do it. So for miss penalty, we need to have the time to replace here. Okay, and here the time delivered to the CPU. If we are talking, we are comparing about hit time and the miss penalty, the difference is quite huge. Because when you talk about miss penalty, it means that you are doing some transaction between CPU with the lower level or you say RAM, right? And the speed of RAM comparing to the speed of cache is quite different. That's why comparing the total time between time and miss penalty, the time is very, very different. So here is some actual value that you can imagine, like the block size. I told you before what is block. It's the section of data. And normally block, the size can be from 4 to 128 bytes. Anyway, the value need to be 2 power of n, all right? So the value can be 2, can be 4, can be 8, can be 16, and so on. But normally the maximum of block size should be around 128 bytes at most. Okay. And then we have hit time. Hit time here we don't count it in the second, but instead we count it in the clock cycle. So here you can see hit time is 1 to 4 clock cycle. And the clock cycle comparing, if you want to convert it to real time, you need to depend on the speed of your CPU. Okay. So hit time here is about 1 to 4 clock cycle. And miss penalty here is about 8 to 32 clock cycle and increasing. So it's still increasing now. Why the miss penalty take up to 32 clock cycle? Because here inside you can see miss penalty have 2 sections. One is about the access time, 6 to 10 cycle. And then the transfer time between RAM to cache and cache to CPU, it take another 2 to 22 cycle. All right. That's why the maximum it can be up to 32 and still increasing. So you see the difference between hit time and miss penalty. Hit time it take at most 4 clock cycle, but a miss penalty can be up to 32. Then so it is about 8 to 10 times different. And then we have miss rate. It's about 1 to 20%. And the cache size is about 1 kilobyte to 256 kilobyte. Cache size can be bigger now. Now it can be 2 to 4 megabyte. Okay. So it's just some value that you can see what is the difference between hit time miss penalty. But remember, this value is now change a lot. Okay, so here, anyway, up until now, do you have any question? Is it good? Okay. So here we talk about how does catch work. And you see here we have two locality or reference, the temporal and the spatial. Actually, I already explained a lot about this already. In here, you see the block here, block X and block Y. And normally in your catch, it has many blocks. But comparing to the main memory, it have a lot more than the number of blocks in cache. That's because the main memory have a lot of bigger space comparing to cache. Anyway, the size of block need to be the same. Okay. And here we talk about how you organize the cache. It's talk about the architecture. From the previous slide until now, we just talk about what is cache and some key term. Talking some about some block. Okay. But after from this slide, we talk about the architecture. When we talk about the architecture, it meaning that what is the data located inside cache? How do you store the data inside the cache? When you like what is the address inside the cache? And then what is the address format of address of the data inside cache? Okay. So there are a lot of architecture, a lot of method that you can store data inside the cache. Here we talk about the simplest architecture. It's called the direct map. Okay, inside the direct map, we split the data into different blocks here. You see, you can see the line here. So here is the first block, and inside. Okay, so here is the first block, and here is the second block, and third block, and fourth block, and so on. Okay. So inside here, you see the I talked. So here is the memory. Here is the cache. Sorry. So the value of the data at address 0, if you are using the direct map cache, it's mapped into the block 0 inside here, inside the cache here. If you are in the data is in block 4 here, it mapped to block 0 here. Okay. So here is the block, here and it's the block. All right. In the direct map cache, the rule to map data between memory into the cache is that each block inside main memory have an exact location inside the cache. It cannot be changed. This means we already know exactly where it should be. Block 0 inside the RAM need to map into block 0 inside the cache, and block 4 here map into block 0 inside the cache. And when you say block 4 here, because there are 4 blocks in cache, but if the cache here has more than 4, imagine that it has 8 blocks in cache. So the number 0 and the number 9 of the block in RAM will be mapped to the same block inside cache. You can see the next picture here. It's more easy to understand about this. For the example, we have only 4 blocks, and inside this example, we have more than 4. Imagine here we have 10 blocks. Okay. Block 0 of main memory is mapped to the block 0 of cache, and the block 10 of main memory is also mapped to block 0 of cache. And why here is block 10 and in the example block 4? That is because the cache size is different. In the previous example, cache have only 4 blocks, but in this example, cache have 10 blocks. Do you understand? So let's say the cache have 20 blocks, meaning that block 0 of main memory and block 21 of main memory will have will be mapped to the same block, which is block 0 of cache. Okay, so this is the rule of the direct map cache. Okay, so here is some example. Okay, actually I already talked about this. And the table you see here is the table representation of cache here. In here you see only the block 0, block 1 until 9. But when you go closer to the cache, you can see that inside cache there are different type of data that is stored. The number here represent the block number 0, 1, 2, 3 up until 9. If we talk about our example here. And inside each block there is a tape. Each block consists of multiple word or multiple byte if the word size is 1 byte. So it consists of multiple byte of data. And then it consists as well the valid bit. Valid bit represent the fear to tell that each block is valid or not. If the block have one valid bit, it means that the data inside is valid. And if the valid bit is 0, the data inside is not valid. So when CPU make a request to cache, it needs to check the valid bit first to see if it is 0 or 1. If it is 0, meaning that the data the CPU 1 doesn't locate it inside the cache. So it needs to go search inside the RAM. Okay. Based on this table, you can convert the memory address into 3 sections. The first section is the tag referred to here. The second section represent the block number, okay? Because you need to know the data that CPU1 located in bit block. So here represent the block number. And the last one is represent word. Word here meaning the offset, or you say the index of word inside each block. Because you see inside one block there are many data. So when CPU want to request for one data, it is not requesting the whole block, but only which one particular data inside that block. That's why we need to know which one of that data that the CPU wants. So here is the address that CPU passing from get from the instruction, and it may request to the memory with this memory address. And then if the cache is direct map, you need to convert that memory address into this section. Okay. You will see in the exercise after that to see what is this 3 section mean. Okay, so here is another representation of the cache. It's similar to this one, but in another format. Okay, we have the valid bit here. Here valid bit, and here is the tag. Okay, tag, and then we have the word. Okay. So here's some example. Assume we have 32 bits of memory. 32 bits of memory here refer to the address side of the memory. Okay, so you can see the address here 0 until 31 because we have 32 bits, 0 to 31. And in this section, we call it cache index. And this section, we call it cache tag. Cache index here include, in case we are using the direct map cache index here, include the block and the word. Okay. And the remaining section, we call it cache tag. And the cache index here, normally the size is equal to the number of data that can be located inside catch. Okay, so let's say that the catch size is 2 power n. Okay, so that the number of bits inside the catch index is 0 to n. Okay, and the remaining from 32 minus n represent the catch tag. Okay, you will see the detail about this in the example below. So maybe we can skip this to exercise. It's simple. Let's just finish this one. It's an example about the catch access. Here represent the maze. So imagine that inside the catch here, the table refer to the catch. See? This is the valid bit, this is the tag, and this is the data. So if we access to the memory address 0001, you see here, 00 refer to tag, 01 refer to data. It go to find, it find the tag and the set bit, the valid bit. If it cannot find it, it will be marked as miss. Okay, so when you cannot find the data, it marked as miss, and then you need to copy the data back to the catch. So this section refer to the access when the catch miss, and this section refer to the access when the catch is hit. Okay. So let's do some exercise to understand the schema that we talked in the previous slide. All right, so we will do this exercise. I will use the draw.io to draw it out. Keep this. Okay. So here the exercise representing how CPU access to catch, and how you can locate the data inside catch, and how it is mapped between catch and RAM. About the exercise one, actually you can find the exercise inside our ebook as well. There are a lot of exercises you can find in there, and you can practice with it. So for the exercise, suppose that we have a computer using the right map catch, which has two power 20 volt. Okay. So let's draw a catch here. Our catch is the right map, so I mark it as the right map catch. Okay. If we use different method to do mapping, you need to apply different method as well. So that's why I need to mention the name of the catch. And with this catch, the size is do we have the size of the catch here? The 2 power 20 here is the size of main memory, not the size of catch. Okay. Using the right map catch has 2 power 20 volt of main memory. So the 2 power 20 here is the size of main memory. Okay, here is the main memory. And it has 2 power 20 volt. So do we have something draw here? Let's just get here. So about 20 volt. Okay. And then our catch has 32 blocks. Okay, so in our catch here we have 32 blocks. Do you remember what is block? From our slide before. The block is the combination of data. So inside the block, it has some data inside. Like it mentioned here, each block contains 16 words. Okay. Okay, just put it here, meaning that there are many more blocks. And inside each block, it has 16 words. Like this. This refers to one word, okay? So this is another word. And this is another word. And many more. Okay, just put it like this. But in total, you have 16 words here. So here I mark it 1. No, it should index it from 0, 1. 2, no, here is 1. Here is 2, and here is 15. Okay, because we have 16 words inside one block. Okay, and here is our block. So our kite have 32 blocks. So this one should be the block 0. Okay, and this one should be the block 1. And this one should be block 2. And the last one should be the block 31. Do you understand what I draw here? Any question? Okay. I just draw what the instruction told us. Okay. And then here is the question. How many blocks of memory are there? Okay. The question here is that inside this main memory, how many blocks inside this main memory? Anyone can tell me how many blocks inside this main memory? Put it like this. Yeah. Okay. How many blocks inside this main memory? If you cannot calculate the number, just tell me how to calculate it. How can I find the number of blocks inside the main memory? So one. Let me call some name to have some activity. David. David. No. So you come, but you don't listen to me. Kim Ha. Kim Ha, are you here? If you cannot speak English or whatever, just speak Khmer. Lina, Kim, I see your message, but I need you to talk, not just message. Lina, are you here? Kéo Lina. Or maybe I should call the attendant. No one is here. So pin. So yes, so the question here, how many blocks inside the main memory?
Cô chúng ta mà sơ toán hả?
Okay. I ask someone else then. Any volunteer then? Yes, so let's just continue. So to find the amount of block inside the main memory, you need to know, like I said before, from the previous slide, I told you that the size of block inside the cache here is equal to the size of block inside the main memory. So from this, you can tell that the size of block is 32 words. Here you see, where each cache block contains 32 words, meaning that inside one block of the cache has 32 words. Okay? And because of the size of the block inside cache and the block inside RAM is the same, so you can tell that here in RAM, it can also contain 32 16 words. Okay, so the size of one block inside RAM also has 16 words. Okay, so I copy here, put it here like this. Okay, because of the size of block is the same, cache has 16 words, so RAM also has 16 words. And you see that here, RAM has 2 power 20 words in total. To find out how many blocks inside, you can just make a division. Here, you can have block equal to 2 power 20 divided by 16, right? Because one block has 16 words and the memory contains 2 power 20 words. So you can just divide by 16 to find out how many blocks inside the RAM. Okay. And then we need to find the result. So 2 power 20 divided by 16. To make it easy to do the division, can convert to exponential the same. Here, divide by 2 power 4, right? 2 power 4 is 16. Okay. So the division, the result should be 2 power 16 block. Okay. So the answer for question A is 2 power 16 block. And then we have the question B. What is the format of main memory address as seen by CHUN? Why the question is like this? Because you know, CHUN is just some representation of the RAM. So when CPU try to request data, it need to locate inside the CHUN first before going to look inside the RAM. In another word, what CPU has is the memory address. It doesn't know that the data is located inside the cache or it located inside the RAM. It doesn't know. What it has is the memory address. Okay? It's just that if the memory is inside the cache, how to locate it? We need to convert it into a format which is the same as the cache architecture. Okay? But if the memory is not inside, if the data is not inside the cache, but inside the RAM, it needs to convert it into another format which is represent the data inside the memory. So what we have is just one single address, but it can be converted to different type of address format. So the question here, with that address, with that memory address, how it can be converted into our cache here. Okay. From the presentation we have, we see that see which one is it here. I told you that when it maps the data from RAM into cache, it needs to convert into 3 sections: the type side, the block side, and the word side. Okay, and word here is the section which is used to find the word inside one block. The section here is used to locate the number of blocks that the data, the block of cache. Okay, and the type here is used to compare the data when we want to search for the block. So to have this 3 section, we need to know how many blocks inside the cache, how many words inside the block, and how many bits total in the main memory here. So to do that, we need to split it into 3 sections. One is the take, and the one here is the block, and the last one is the word. So here is question 2. Let me copy and pass it here. Question B. Format of main memory seen by direct map cache. Okay. And like I said, because we are using direct map cache, we need to convert it into 3 sections. The section is the take, and then the section is the block, and then the last one is the word. So, first we need to find how many bits of this main memory address. Okay. From the question that we have, we have the question. Okay, from the question, you see that in main memory, there are 2 power 20 volt inside this memory. Okay, so here, let me draw it out. Okay, and pass it here. Okay, this is the first block, and this is the another block, but it is in the last one. It should be 2 power 16 minus 1, right? Because we start address from 0. So the number here refer to the number of blocks. And if we talk about the address here, 0, 1 to 16, this should be the address here should be 2 power 20 minus 1. Okay, you get what I mean? Change the order here. Like this. 2 power 20 minus 1. Why 2 power 20 minus 1? That is because the main memory has 2 power 20 volt inside it. Okay, and here it should not 2, but something like, let me think a bit, this should be 2 power 20 minus 16. Yes. This should be 2 power 20 minus 15. And this should be 2. This should be 2 power 20 minus 14. Okay. And the last one is 2 power 20 minus 1. And why minus 1? Because we have data starting from 0 here. Okay. So in short, we can tell that inside our memory here, we have 2 power 20 volt, and each volt has one address. Okay. Each volt has one address. How many bits that you need to encode that 2 power 20 volt? How many bits? Can you tell me? Let's get some other example. If the 2 power 20 is so big, it's too big for you, imagine that in our RAM only have 2 words. Let's say in our memory only have 2 words. Okay. And then inside this 2 words, if we ask the same question, how many bits that we need to encode these 2 words? The answer is 1 bit. Okay. And why 1 bit? Because in 1 bit, you can create 2 different values, which is 0, and another value, which is 1. Okay. So you can use value 0 to represent the first word, and you can use value 1 to represent the second word. In another word, you only need 1 bit because 1 bit has 2 possible values, which is 0 and 1, right? So what if the memory has 4 words? How many bits that we need to encode the 4 words, the address of the 4 words? Okay. In this, we need 2 bits. And why 2 bits? Because with 2 bits, you can have 4 different values, which is 0, 0, 0, 1, 1, 0, and 1, 1, right? So we have 4 possible values, and each value can represent one address of one word. Okay, and as we have 4 words, so we need 2 bits. Okay? Based on this, you can create some formula. Formula here is 2 power n. Okay, if you have 2 power n words, so you need n bit to encode all the word inside. Is it correct? Like this? Same, right? 2 power, let's say, here 2 power 1, right? 2 power 1. So we need 1 bit. Here 2 power 2 equal 4. So we need 2 bits. If you have 8 words, so you need 3 bits because 8 words equal to 2 power 3. So if you have 2 power n words, you need n bit to encode each address of each word, right? So in here we have 2 power 20 words, right? So the answer here, we need 20 bits to encode all the word inside our main memory. Okay. So our memory address is composed of 20 bits. So what you need to do after that, you need to find out the number of bits that you need to encode all the word inside one block. And then the same thing, you need to find the number of bits to encode all the block inside the cache. And here is for the remaining. Okay. So from our question here, each block contains 16 words. So like the same rule here. In one block we have 16 words. So how many bits that you need to encode each address of that 16 words? How many? Yeah, too quiet. 16, right? Apply our rule here. 16 equal to 2 power 4, right? So we need 4 bits here, right? Because there are 16 words inside one block. Okay. And then for this block, the same thing, but the block here doesn't refer to the memory, but refer to the number of blocks inside our cache here. In our case, we have 32 blocks here. See, 32 blocks here. So we need 5 bits to encode all the blocks inside our cache. And the type here just simply do some subtraction between 20 and 9. So we need 11 bits for the tape. The tape here for the remaining tape. Okay, but for the MSB, not LSB. The most significant bit is just for the tape. Okay, so here is the answer of question B. And then the question C. Question C.
Not some clear more question 2 nữa.
B นี่ไงสนุก B นั่นเหมือน
Bạn.
Let me speak Khmer a bit now. ក្នុងករណីសំណួរ B នេះខ្ញុំអានោះយើងត្រូវយល់ពីសំណួរសិនតើគេចង់សួរពីអីក្នុងសំណួរ B ហ្នឹងគេចង់សួរថាតើនៅពេលណាដែល CPU បោះ address របស់ RAM មួយមកមាន address មួយរបស់ RAM ណាហើយ CPU យកអា address ហ្នឹងទៅរក data នៅក្នុង cache តើ address ហ្នឹងត្រូវ convert ទៅរបៀបណា convert ទៅរបៀបណាដើម្បីអាចឲ្យ CPU locate data នៅក្នុង cache បានអូខេអាហ្នឹងជាសំណួរ ហើយដើម្បីធ្វើអញ្ចឹងបានយើងត្រូវ convert យើងត្រូវ convert memory address ដែលយើងមាននៅក្នុងដៃហ្នឹងទៅជា format មួយអាស្រ័យលើប្រភេទ architecture របស់ខាច់របស់យើងគឺប្រើ direct map អញ្ចឹងក្នុងករណី direct map structure របស់ memory address ត្រូវចែកចេញជា3 section section ទី1គឺជា word section ដែលជា section មួយ represent ទៅឲ្យពាក្យទាំងអស់ទៅឲ្យ word ទាំងអស់ word នោះគឺសំដៅ data ណាគឺសំដៅ data ទាំងអស់ដែលមាននៅក្នុង block មួយអូខេ section ទី2គឺជាចំនួន bit ប្រើដើម្បី identify block ទាំងអស់ក្នុងខាច់អញ្ចឹងប្រសិនបើយើងមានប្រមាណខាច់របស់យើងមានប្រមាណ block យើងត្រូវ convert វាទៅជាចំនួន bit ចំនួន bit data ដែលជាចំនួន bit នឹងប្រើដើម្បី identify block ទាំងអស់នៅក្នុងខាច់ហើយសម្រាប់ section ចុងក្រោយនេះវិញគឺជារបស់ដែលនៅសេសសល់តែសេសសល់ពីចំនួន block បូកចំនួន word ហើយទៅដកជាមួយនឹងចំនួន bit សរុបទាំងស្រុងទាំងអស់របស់ memory អូខេអានេះបើចង់យល់ច្បាស់តទៅមុខទៀតថាស្អីគេ type block word ហ្នឹងយើងចាំដល់សំណួរ C យើងនឹងអាចចាប់ផ្ដើមយល់ហើយព្រោះសំណួរ C គឺគេសួរថាតើធ្វើម៉េចយើងរក data ហ្នឹងបានអញ្ចឹងពេលហ្នឹងយើងត្រូវយល់ថារបៀប convert របៀបម៉េចអូខេឥឡូវយើងគ្រាន់តែចាំប៉ុណ្្នឹងសិន type block word អូខេហើយបន្ទាប់មកដំបូងបំផុតដើម្បីរក type block word ហ្នឹងបានយើងត្រូវហៅចំនួនសរុបសិនចាប់ដើមដំបូងបំផុតយើងត្រូវ address សរុបសិនaddress memory address ហ្នឹងមានប្រមាណ bit សិនអូខេហើយដើម្បីរកចំនួនថាតើ memory address របស់យើងមានប្រមាណ bit អាហ្នឹងវាអាស្រ័យលើចំនួន data ទាំងអស់ដែលមាននៅក្នុង memory ព្រោះថាយើងត្រូវដឹងថា data មួយរៀងរាល់ data ទាំងអស់នៅក្នុង memory គឺតែងតែមានមួយ address ដូចផ្ទះយើងអញ្ចឹង data មួយដូចផ្ទះមួយអញ្ចឹងហើយផ្ទះមួយគឺមានតែមាន address ថាទោះតែមាន address ហ្នឹងគេរកឃើញមកអញ្ចឹង CPU អាស្រ័យលើ address ហ្នឹងដើម្បីទៅរក data ហ្នឹងតែ data មួយត្រូវតែមានមួយ address អូខេតោះហ្នឹង data មួយត្រូវតែមានមួយ address ប៉ុន្តែនៅក្នុងម៉ាស៊ីនកុំព្យូទ័ររបស់យើងនេះ CPU ស្អីក៏ដោយ memory ក៏ដោយស្អីក៏ដោយ data ដែលវា store ជា binary វាអត់ស្គាល់លេខ1 2 3ទេវាស្គាល់តែ binary 0101ទេអូខេអញ្ចឹងយើងត្រូវដឹងថាធ្វើម៉េចដើម្បីអាចឲ្យ data មួយមានមួយ address បានយើងត្រូវប្រើចំនួន transistor ប្រមាណប្រសិនបើ transistor មួយស្មើនឹង1 bit ណាអញ្ចឹងក្នុងករណីរបស់យើងគឺត្រូវការ20 transistor ឬក៏20 bit ដើម្បី identify ពាក្យទាំងអស់នៅក្នុង RAM របស់យើងហើយហេតុអីបាន20 bit ដោយសារតែ RAM របស់យើងហ្នឹងទំហំរបស់វាគឺ2ស្វ័យគុណ20នេះ2ស្វ័យគុណ20 W នេះហើយហេតុអីបាន20 bit នេះខ្ញុំបញ្យល់ពីខាងក្រោមនេះមកនេះបើសិនបើវា2 W យើងត្រូវការតែ1 bit ទេដោយសារតែ bit មួយវាមាន value 2គឺ value 0ហើយ value 1មិនអញ្ចឹងអញ្ចឹង value 0តំណាងឲ្យ address ទី0 value 1តំណាងឲ្យ address ទី1ក្នុងករណីយើងមាន4ពាក្យនេះវិញយើងត្រូវការ2 bit ដោយសារតែ2 bit វាអាចមាន4 possible value គឺ00 01 10ហើយនិង11ឃើញអត់អញ្ចឹងយើងត្រូវការ2 bit ដើម្បី identify ពាក្យទាំង4នៅក្នុង memory ហ្នឹងអញ្ចឹងអាស្រ័យលើឧទាហរណ៍ដែលខ្ញុំឲ្យហ្នឹងយើងអាចកំណត់ចេញជា formula មួយបាន2ស្វ័យគុណ n បើសិនបើ memory របស់យើងទំហំ2ស្វ័យគុណ n word ឬក៏2ស្វ័យគុណ n data គេថាយើងត្រូវការ n bit ដើម្បីទៅ encode address ទាំងអស់របស់2ស្វ័យគុណ n word ហ្នឹងអូខេអានេះគឺរបៀបរកចំនួន bit ហ្នឹងពេលដែលយើងយល់អាហ្នឹងហើយយើងមក apply នៅក្នុង rule របស់យើងនេះយើងដឹងថា memory address របស់យើងគឺ20 bit សរុបទាំងអស់អញ្ចឹងយើងត្រូវរក word នេះមុនគេនេះ word នេះមុនគេយើងដឹងថានៅក្នុងមួយ block ប្រធានរបស់យើងណាមួយ block គឺមាន16 word ក្នុងមួយ block គឺជា16 word ហើយតែដឹងថា block ហ្នឹងគឺជាបណ្ដុំនៃ word អូខេបណ្ដុំនៃ data អញ្ចឹង word មួយមានមួយ address មិនអញ្ចឹងអញ្ចឹងក្នុង section ចុងក្រោយខាងស្ដាំគេហ្នឹងគឺថាតើយើងត្រូវការប្រមាណ bit ដើម្បី encode word ទាំងអស់នៅក្នុង block chứ biết sầm nón tại đái đối nhau mà bây giờ pin đi mà chứ còn nó những gì compare cho mùi memory thằng mút nó nhưng compare tới cho mùi block mùi thì chứ block vào chứ cứ miếng đọc vào mùi vợt này thì chứ là mấy encode vợt mùi là không block đây nên chúng nó đọc vào mùi vợt chứ thời cá tại 4 bit thế ok 4 bit đấy làm mấy encode đọc vào mùi vợt năng trọng đồng chứ bácจะ say กระดาษรุ่นไหนđấy 4 bit zone mũi thì ly thằng áo mấy bạn đọc vào mũi case mình chẳng trong cái thá như thời cả 4 bit làm mấy encode vợt thằng áo là nó block nó section TP nè section TP nó cứ pra làm mấy identify block thằng áo là nó khai bảo dưỡng miếng 32 block nè 32 block khai chẳng để sao block mũi có vì miếng address bảo vi mũiได้để sai chạy chỉ block á chẳng như thời miếng address mũi tầm nào ai block này vì miếng 32 block chẳng pi sẽ con pra mình mà 32มันเนี่ยpiส่วน4สักกับmũi piส่วนpra mình mà 32chẳng hai bạn những thời cả 5 bit làm mấy encode block nó là con khaiคือต้องการในไทยเว้นคือจีระบบได้ในสัดส่วนปรับให้ดอกปุ่มเจนtớiมันสำหรับมวยโอเคสนุกบีตอนออก
ตอนใช่
chẳng dương màสำนวน C นั่นคือถ้าบ่ตอนโยธาสังเกตไทยสังเกตบล็อกสังเกตวอร์ดสำนวน C นั่นคือยังจับตามโยอะไรตัวท้าแต่ใบหกบ้านตัวอะไรdươngโยละใบน่ะ okay so coming back to the question C question C here is about imagine that you want to find the data inside the cache with address 0db63 okay the value here is in hexadecimal okay the value here is in hexadecimal so imagine that you have this address and we want to find the location of this address inside the cache. What can we do? Okay so here let me type some question here locate that data in cache with address 0db 16 0db 53 and it is in hexadecimal okay okay so the question C here and how can we find it because if we are looking it into the RAM it's quite easy you can just compare this address with the address bar inside the RAM and that's it it's simple right if we want to locate data inside RAM you just have the address you compare it you get it but when you copy into the cache it's not simple like that because the cache is very small compared to RAM. So the data when you copy from RAM to cache, it can be in anywhere, depend on the architecture of the cache. Right? So in cache, our cache is using the map. When you copy the data here into the cache, you need to follow this structure in question B. Okay? Each block inside the RAM has a specific location inside the block. You cannot put anywhere. When you copy to cache, you need to place it in some specific location. You cannot change it. This is the rule of the direct map cache. So if you know the structure, you can easily convert it into real location in the cache. And how can we do that? First, you need to convert this number into binary first because computer only know about binary. It only knows 0 and 1, nothing else. Hexadecimal, decimal, it doesn't know anything about that. Okay, you need to convert it first to the binary. So now let's convert it into the binary. I can use some online tool. Just in Google, we can type in a convert hexadecimal into binary. Here, I found this tool. You can use your calculator as well. It's simple. And then input the value 0D B63, right? 0D B63 in hexadecimal. Convert into binary, and you can convert here. Got a value here, right? Copy it and place it back here. Okay, so here is the binary represent 0DB63 in hexadecimal. Okay, but remember that the memory address, we have 20 bit, right? So make sure that this binary has 20 bit as well. So 2, 4, let me split a bit to make it easy to understand. 4, and here another 4, and here another 4, and here another 4. So how many bits do we have? We have 16, right? 4, 8, 12, and 16. So you need to add another 4 bit to make it 20 bit, right? You need to add more 0 in front. Is it correct? 20 bit. We have 20 bit here. Okay. Oh. Okay. So we have 20 bit here. And then you see that the LSB, we call it least significant bit LSB. We have 4 bit of LSB refer to the word section. So let's make some more space, make it easy to see. So this 4 bit is the word section. Okay. This one is the word. It represents the address of word inside one block. Okay, because the block has 16 words, remember? And then the next 5 bits is used to represent the number of blocks inside cache, right? So here I make it more space like this. Okay. It represents the block. Okay. And then the remaining here represent the tag. Okay. So this is the tag. Okay. So after we convert to binary, we can split the bit to different sections as we have from question B. So based on this, what can you tell? What can you explain? What is the location of data with address 0DB63 inside the cache? Do you get some idea now? Based on this, how can you locate your data inside here? Okay. So first, we need to compare tag. If we follow the procedure, you need to compare the tag if the tag exists or not inside this cache. If the tag exists, you need to go to the next step is to compare the block. All right. The tag here must be unique inside here. Okay. So that's why you can compare the tag. So you can say that the data is exactly exists inside the cache, right? Based on its state. But it just know that it's inside the cache. You need to do some more work to look at the actual block. And then coming to here, from 10110 here, you convert into decimal. It is easier to understand. Let's convert into decimal, binary to decimal. And then the value is 10110. So convert it. It's equal to 22, right? So from this, we can say that the data at address 0DB63, which is in hexadecimal, 0DB63, which is in hexadecimal. Look at it. Look at it inside block 22 in decimal. Do you understand what I mean now? And then you know that it's inside the block 22 of the cache, and offset here refer to the index of the word here. 0011 equal to 3, right? And offset 3 in decimal. Okay, so here is the answer. And to let me assume that this block is block 22. So the data here is in block 22 and offset 3. Okay, and this one is offset 0, offset 1, offset 2, and the last one is, no, not the last one, but the next one. Next one is offset 3. Like this. Okay, so here is the data that we want. Let's use another color here. Do you get it now? So if you have this address, if we are not using cache, we go to find the data in here directly. Let me make it smaller. Can move it to this section here. So in case we are not using cache, you can look at the data directly inside the RAM like this, as long as you have the address, and our address is like 0DB63. Okay, if you are not using the cache, you can go directly like this. But when you are mapping that value into the cache, you need to convert into something else. You need to convert into something else like this by placing the data inside some specific location of a block and inside some specific offset inside that block. So you need to convert that value 0DB63 into a format seen by the map cache. And then based on that format, you can find the real location of that data inside the cache. All right. I will send this to you. question? Any question? Okay. So this for question 1, and here question 2 actually is the same. Okay, the same. So I will let you do it now, 15 minutes, and then I will ask someone to answer the question. Got it? We have here the question 2, the same thing. We just change the value here. You see the value change, but it's still the same. And I give you 15 minutes to work on it. After that, I will pick 3 people to answer the question. And hope that you can answer it. So let's get started then.
Teacher, when we convert the hexadecimal to the binary, and how can we know the value of the binary, teacher?
How can we know the value of binary? You mean here? You mean the how do you know that 4 bit here is the bird, 5 bit here is the block? You mean like that?
No, teacher. When you use the calculator on the website, I missed that time, teacher.
Actually, it's easy. You can use any tool you want. Maybe you can even use calculator in your computer. For example, here, I have the calculator here. I can click view like a programmer like this. I can input like this. But as I want to copy it here, I cannot copy from here. That's why I say in the browser, you can just type convert hexadecimal to binary. And then from here, you can click on hexadecimal and click to binary here. See, and then you input 0, D, B63, like I told you before. Click convert here. And then here is the binary. All right. Copy it. Come in here, like I do before. And then I need to add 0 in front to make sure that in total you have 20 bits. You need to make sure you have 20 bits. Okay?
Got it, teacher. Thank you, teacher.
So your turn now. You are working on the question 2, the same thing. I give you 15 minutes to do that. Actually, we don't have 15, maybe just 10. I need to correct it, so just 10 minutes.
Look cool.
បាទចង់សួរអី
នៅពេលដែលលោកគ្រូហៅវត្តមាននៅខាងខ្ញុំដាច់អ៊ីនធឺណិតលោកគ្រូពេលខ្ញុំអត់បានឆ្លើយ
ខ្ញុំមានតែបានហៅវត្តមានណាខ្ញុំបានហៅឆ្លើយសំណួរដែរអត់អីទេតែបានហៅវត្តមាន
បាទគ្រូអរគុណច្រើន
ខ្ញុំពួកយើងធ្វើលំហាត់ទី2ណាខ្ញុំຕົកពេលឲ្យ10នាទីធ្វើដូចគ្នាមួយនេះអញ្ចឹងហើយអាចមើលក្នុងឆាតនេះបានខ្ញុំ send ឲ្យពួកយើងមើលហើយដូចគ្នាអញ្ចឹង Okay, so how is it? Exercise 2, question A. This. Here. Okay, question 2, exercise A, how many blocks do we have? Let me call some name. កុងសុភាព សុភាព សុភាពនៅអត់សុភាពលើឆ្លើយមិនក៏មិនឆាមិននិយាយចាំបាច់ឆាទៅអីឥឡូវឆាក៏ឆាដែរឥឡូវប្រហែលតើថានិយាយអត់ហ៊ាននិយាយលើទី 2A មិនប្លុកនេះទៀតឆាតក្នុងនោះក៏បានដែរឥឡូវថាមិនអត់ឆ្លាតបានឥឡូវឆាតមកនោះ A នេះ 2A how many blocks of main memory are there សួរអ្នកណាក៏អត់ដឹងមកអញ្ចឹងដោយតាល្មាត់ខ្ញុំធ្វើឲ្យការឲ្យហើយនេះឥឡូវ
2 power 27 teacher
2 power 27
yes
okay let figure it out so here to find the number of blocks inside main memory we need to take the number of words inside which is 2 power 32 so I change it to power 32 and divide with the number of words inside one block, which is 32 words. So 32 words, and we convert into something like this. 5 for 32. So the answer is 2 power 27. Yes, which is correct. Oh, it got here. Okay. So the question A. The question A, the answer is 2 power 27 block inside the main memory. So question B, what is the format of memory address as seen by CHUN? So the question here, we are talking about this. How many bits for the word field, how many bits for the block field, and how many bits for the text field? Any volunteer? Yeah.
Teacher, for word it have 5 bit and block 10 bit and take 15 bit teacher.
Yeah, again, what? 5 for?
5
5
and block 10 block teacher. And take 17.
17. Okay, so thank you. Let's figure it out. And here it should be 32, right? Because we have 2 power 32 words inside our memory. So because in one block we have 32 words, right? 32 words, which is equal to 2 power 5 words, right? That means we need 5 bits to encode all the words inside one block. So this one is correct. And then we need to figure out how many blocks inside our cache. Okay. From here, you see the cache is composed of 1024 blocks, which is equal to 2 power 10 blocks. Okay, that means we need 10 bits to encode each block inside our cache. So this means it is correct as well. Here, but I wrong 32. And for the take bit take here is the bit which is remain from block field and word field. That means we have 32 minus 15, which is 17 bit. Okay, so your classmate that we have 17 bit for take, 10 bit for block, and 5 bit for word is correct. Okay. So the last question here, question C. What is the address which kite block? Okay, which kite block in kite that the address T3 FA is mapped to? Volunteer again. Maybe someone else? The same person again and again. 63 FA. Okay, 63 FA. When you map it into our cache, which block it is located to? Like we do before, don't forget to convert it into binary here. T3 FA. Convert, you get value. Stamping back here. Replace it here. Make sure that it has 32 bits. So now we have 4 here, 4 here, 4 here. So we have 16 bits now. We need to add more. Okay, let me copy like this. Okay. 16, and we need one more. Like this. Make sure you have 32 bits. Anyone have the answer before I continue the question? Which block here? You should be able to do it right after this. Here, 5 bit. See? So the 5 bit here refer to the board. 5 bit here. And then we have 10 bit here inside. Refer to the block 2, 4, 6, 8, 10, right? Right now, yes. This should be block. Right. Whatever. Yeah. This will be block. Yeah. And the remaining here should be the take. Okay. Okay. So the answer, you should be able to answer this now.
The block located in block number 799.
Okay, 799. And then the offset?
26.
This. Okay. So what you do is just convert this back into the decimal. Copy it here. Where is it? From binary
26, teacher.
26. Okay, then. So the block here 799, that's correct. And the offset we need to copy this, the last 5 bit here. Copy it and convert it to the decimal, which is 26. Okay, that's correct. Okay. So the question is quite simple actually, if you understand it. And if you want to do some more, a bit more harder exercise, you can refer to the ebook. Okay, thank you, Supin. Actually, you can also capture screen, take picture and put it here so to share with your friends. And for the harder exercise, if you're interested to do some more exercise, you are welcome to do so as well. You can find it in the ebook. I already put the ebook inside and go to this one, John and Bartlett here. And you can find the exercise in page 200. Something I forgot. Let me find it. Chapter 6. Chapter 7. This one is chapter 7. Here, the exercise in here. Actually, the exercise you have just done is also taken from here as well. Okay. This is the exercise number 1 that we have done. This is the exercise number 2 that we have done. And we have exercise number 3, number 4, number 5, until number 16, I think. But some of the letter exercise related to all the subject. For now, you haven't learned about it yet, so maybe you cannot answer it. But you can still do some exercise from number 3, number 4, like this. Number 3 is using another kite, which is fully associative, and you can find it inside the slide as well. Fully associative, and here it should be the set associative. So if you can do it, go ahead. If not, we can do it together later. And if you don't understand my lecture, maybe it's too fast, too short, or whatever, you can find the detailed explanation inside here as well. Inside chapter 6. Okay, the ebook is quite long, but it's very detailed and easy to understand. So in case you cannot understand what I say, you can ask me again, or maybe you can look into this ebook. All right, everything is coming from here in chapter 6 here. Okay. So today, thank you for your attending, for your participation. And we will see each other again next week. And don't forget, the project about internet programming is already start from next Monday. So talk to your team member, make sure you at least know each other you have a way to communicate, maybe create a Telegram group for each group and then communicate, divide the task, make sure you have at least one leader so that I can talk to, all right? We have only 3 months, so don't do it in the last 2 weeks. You cannot do that. So thank you for today. Bye-bye.
Excuse me, teacher.
Yes.
I would like to have a screenshot